Hi, welcome back to AP Physics C, Unit 3, the Work Energy Power Unit. So in this video, we're going to focus our efforts on power. So power is connected to the first two topics that we talked about, which is work and kinetic energy, and then the work energy theorem. So at this point in time, we have not talked about the relationship with anything in regards to time. So when we start bringing that in, we look at the rate at which work is done, or the relationship between work done and the time interval. We're going to call that average power. So power average is going to be delta W over delta T. So what this is in actuality is the slope of a work time graph, right? Because you see that this delta notation, right? Anytime you have change in quantity over change in quantity, it's going to be a slope of those two quantities. When we look at it really is, especially here in Physics C, is that we look at what we call instantaneous power. And it's defined as, not the rate, it's not like they ate again, but it's the rate at which work is being done. Or we say the limit of power of time intervals, not intervals, sorry, I keep approaching zero. And so this now looks more like calculus. So it would be simply dW dt, right? Easy way to distinguish the two. If you're given work as a function of time, then that's probably going to be, and you have to find power, that's probably going to be your instantaneous. If you're just given, like work is done by this force, it's probably going to be an average, all right? But we can also redefine work by saying it's the integral of power dt, right? And so power, not delta t, but dt, right? And so this will tell us that work is the area under a power versus time graph, if that ever pops up on the test. But we can also rewrite this equation because through, work being force times distance, but then if I were to substitute this into an equation, you end up with a delta x over delta t, which is just simply velocity. And so power can also be expressed in terms of force and velocity by a dot product. So it's force dot velocity, or the magnitude of F times the magnitude of V cosine of the angle. And this is the equation that we're going to use here in our example problem. So let's take a look at that now. So here we have a car, a 1,200 kilogram car going up a 15% grade at 90 kilometers per hour. And we're going to assume that 25% of the power that it needs is dissipated overcoming air resistance and friction. Okay, so what we're saying is 0.75, the power they need, right, is going to be our F dot V. But we need to determine what force is actually doing this power. And that's going to come from our, essentially unit 2 by saying that, the force that's doing the power is going to be the X component of the weight, right? And so you would do like a free body diagram, okay? And note that these two, if going at a constant velocity, would have to balance each other. So that's where you get F equals mg sine theta. So that's going to go in for our F. Now, what about our velocity? So our velocity or speed is given to us. It's 90 kilometers per hour. So we would need to convert this to meters per second. So 1 kilometer is 1,000 meters. 1 hour is 3,600 seconds. And that would give us a velocity of 25 meters per second. Okay, but now we need to figure out the angle. And the angle comes from the grade. So the 15% grade is your rise over your run. Okay, and so we can do the inverse tangent of our percentage converted to a decimal. That'll give us our angle. And so a 15% grade is an angle of 8.53 degrees. Okay, so now we have really almost everything that we need to do, but the last thing we'll have to do is divide both sides by 0.75, because remember, it's only going to use up 75% of the, right, of the, or 25% of the power, which means it's going to have, 3/4 of that power left. And so now I can say power equals mg sine theta times my velocity over 0.75. Now I can plug in my numbers. So 1200 times 9.8 sine 8.53 times 25 divided by 0.75. And so how much power does this car need to make it up this 15% grade? Well, it's going to be 58,144 watts, or if we divide that by divided by 1,000, you get 58.1 kilowatts. Okay, but remember, more common unit is horsepower, where 1 HP is 746 watts. So you can figure out how many horsepower it would require. Okay, so now in the next video, we're going to shift from talking about kinetic energy, work, power, to now starting putting together with potential energy, conservative forces, and conservation of energy.